All right, dude, we are live. What's up, guys? This is Dem Keys, and today we are going to continue learning about pulse width modulation in ESP32. Today, we are probably going to be making a lot more progress on the higher level PWM stuff as compared to the past couple of streams where we've mostly been focusing on low level stuff. And just yesterday, um, I ended up going a little too deep in trying to, in my quest to try and understand how the system is working on a lower level. And then I kind of had to stop myself before I ended up spending way too much time on something that didn't need all that much time spent. Um, by the way, ever since I started using WesTerm, um, and I set up this new layout where, hold on, I need to um, refresh this stream. Okay, there you go. Ever since I set up this new layout, the new layout, quote unquote, in this case is I have this, what do you call it? I have So I have these three windows. I have these three panes. This is one WesTerm tab, and within this tab, I have three panes set up. One pane is for the. I should keep this in mind that I actually do have the mouse cursor being captured even on this side where this entire feed is being captured, because these three panes that you're seeing here, these three panes are running in WesTerm, and that is running on my Ubuntu desktop. On that desktop, I have an RTMP server running, um, and I also have OBS that is capturing. Well, I have OBS running that's capturing the video feed, which in this case is just this WesTerm terminal. It's capturing that video feed and streaming it to the RTMP server that's running on the very same system. And then on this laptop that I'm streaming to Twitch from, on this laptop, I'm accessing that RTMP feed over the network. Why was I explaining this? Oh yeah, I was just trying to explain the I was talking about the WesTerm thing. So previously I was using the Kitty terminal, and even there I'd set up something similar. It was pretty much this exact same thing. It was three panes. One of them was the matrix rain. The other two were TMUX sessions, and that's what was being streamed. Oh, additionally, there's the webcam, which is also being captured on the other machine. Um, But yeah, ever since I've set this new thing up, I've been having some trouble deciding whether I want. I've been having trouble deciding what size I want these panes to be. Um, it kind of seems like I should try to maybe make this pane a little bigger. That makes a little more sense to me. So the upper pane can be a little smaller because it doesn't. I don't often do a lot of like work. So how do I say this? If I'm coding, for example, I'm usually doing it in the lower pane. So it's in the tmux session that's running in the lower pane. I'm not usually doing coding in the upper pane. A lot of times the upper pane is for extra stuff, like if I need to display something, or if I need let's say I want to open up Yahtzee, which I have open right now, or if I want to open up a Python interpreter and type things out there. Usually that's what I'm using it for. So it kind of makes sense for me to maybe make the lower pane a little bigger, so it gives this pane a little more space, and a little more stuff can be visible in that way. And also, I've been trying to decide what size I want this thing to be. Like just now I changed it. I was having trouble deciding what was, a good point uh to or a good size to keep it at, because the matrix range is fine. I don't mind keeping it small because the matrix rain is still showing up, so I don't mind keeping it a bit small. Uh, the two panes on the right side, they require more real estate, let's say. They require to be, you know, seen. So I should be giving them a little more space. But yeah, yeah. So unfortunately, after yesterday's stream, I didn't manage to read the Forest Mems book. I didn't make any progress with analog electronics stuff. I got busy doing some other research. I can't remember right now what exactly that research was. There was something that I was trying to do, and I got busy doing research on that. But that yeah, I can't remember exactly what it was, but there was something. And I was busy with that. One thing that I do remember from yesterday. Oh, first of all, I spent some time setting up this. We now have. Actually, we probably had this yesterday as well. It's just that I customized it a tiny bit. I spent some time reading up on the settings for smear cursor, and I realized that I needed a different color for the smear to to make it a little more visible to me. Because at least for me, I can't speak for anyone else. At least for me, when I'm able to see the smear much more clearly, then I get that effect that yeah, there's a trail. And um, from the very beginning, it wasn't just aesthetics. Aesthetics weren't the only reason why I wanted a cursor trail. Aesthetics was definitely a major, like it was a huge thing. I liked the aesthetic of a cursor trail versus, you know, no trail at all. I like the aesthetic going on there. I like the effect. So I that's one of the reasons that I enabled it. But another very important reason was that I would often find myself losing where the cursor is. Like I could be on a line. Fortunately, in NeoVim, there's this line highlighter, so I can this way I can detect that yeah, I'm on so and so line. However, on this line, where exactly is my cursor? If you look at the thing that highlights where the cursor is, it's like it's not all that visible. It's great, like the color that it is right now. That's great. That's awesome. So I don't want to change that. However, um, it's not very. It doesn't stand out. So that's why the cursor trail, it helps, because if I real quick do stuff like this, then I can see where the cursor is, and that way I know that it's there. And then of course there's also the fact that I like the aesthetic of cursor trails. I do wish that they would implement this as a native feature in WebTerm, so then I could turn this plugin off. um, I do wish that they would implement it as a native feature within WebTerm, because, dude, I very much like that feature. Also, I'm kind of happy to say that for the most part, I have pretty much moved over to WebTerm now. Like that was the whole idea. That was the whole point. Moving my workflow over to WebTerm and just using WebTerm as my regular terminal, instead of using the Kitty terminal on one machine and exploring WebTerm on another machine. I wanted to just hurry up and move everything over to WebTerm because I'd already done a good bit of research on it. I'd done a good bit of exploration. I've even learned how to, and I'm still learning. There's quite a bit to explore there. But yeah, I've learned how to configure WebTerm. I've spent some time setting up, custom configs for myself as well. So I wanted to basically just make this my daily driver, and I've succeeded at that. So far, I'm not seeing any, you know, issues that I could possibly run into. They also have this pretty awesome what was it? Control Shift X, I believe. Yeah, they have this nice copy mode. I don't know if the copy mode is really going to show up well in Tmux, but or I don't know if the copy mode is really the best. Um, I don't know if this is copy mode not here. This is copy mode not in what you guys are able to see, but it's in what I'm able to see. So for me to show you copy mode, I'm gonna have to do it here. There. So now you can probably see, actually you can't see the in the bottom left. I was about to say you can look in the bottom left, but then in the bottom left, where the status bar usually shows up, I've kind of there's a browser above it. Let me disable this real quick. There. So now in the bottom left, you can see we are in copy mode, and basically in copy mode, I can select whatever text I want, and I can yank it, or I'm not limited to just, character selection. I can also do entire line selection. Um, I forgot what the thing was. First of all, V is to start this, Shift V is for line, and then Control V is for block. So I can also do block selection, and then just yank Y to yank it. Yanking is basically, copying. But yeah, this is great. This is awesome because um, previously I would have had to open up. So in if I was using the Kitty terminal, I had to map a key to a certain function which reads the scroll buffer, the buffer for that specific pane. It reads the scroll buffer and pipes it into a NeoVim instance. I don't remember if it creates like a temporary file or something, but you can pipe data directly into NeoVim as well. So yeah, it would just pipe the data into that, and you could additionally add in options to make it like a unmodifiable buffer or something like that. So basically a read-only buffer, and that's how I would copy text from uh, the terminal's output if I need it. But now I just need to hit Control Shift X and enter copy mode, and then select whatever I want, and then I'm good to go. This is great, dude. This is amazing. Like, I'm discovering so many things about WesTerm. It's wild. Um, Also, I'm slowly starting to like wrap my head around a sort of, I guess you can call it, a philosophy of WesTerm. It's that, okay, they've provided you with the terminal. However, you're kind of expected to customize it to your liking. You're expected to customize it to suit your needs. Give me a second here. I'm just testing or checking. Sorry, I'm just checking if a change that I made shows up. Yeah, there it is. Okay. Yeah. So what I'm slowly starting to realize is that WesTerm is one of those terminals that's kind of like NeoVim, where in that um, it provides you with like a lot of functionality. There's a lot of functionality in WesTerm, dude. Believe it or not, there's a bunch of functionality in WesTerm that's not even key mapped. So like you would have to do Control Shift P to open the command palette, and then type in the function, or type in whatever the name is of, whatever function you're trying to call, and then select it from there. You'll notice that there's a bunch of functionality that hasn't even been key mapped. So if you need certain functionality to be key mapped, you have to define the key map yourself. And Western makes it very easy to define key maps within the config file. In fact, you can do slightly sophisticated key mapping as well, because you're not just limited to the keys that you're not just limited to simple stuff like Control Shift Alt and then whatever keys. You can also add in the leader key. So you can define a leader key, which in something like NeoVim, leader is space. So you can do space and then let's say window, and say you want to split vertically, right? That's the leader. That's the words. That's the leader key in NeoVim. In Tmux, the kind of sort of equivalent of that is what they call the prefix key, and by default that's Control B. So if I hit Control B, you'll see in the bottom left. Oh, you don't see it there. Okay, I'll have to do it here. If I hit Control B here, yeah. Oh, you guys were able to see it. Okay. Were you? No, I don't think so. I have to do it here to show you. So, if you look in the bottom left of the, how do I describe this? If you look at the pane that's in the bottom right, and then you look in the bottom left of that pane, you'll notice it says, actually, my mouse is visible, right? Yeah, I can just do that. So you can see the mouse here. If you look here in this bottom left of this pane, next to other laptop, you'll see this sort of icon. The icon is currently red. That's because I've hit Control B. So that's how you know that the prefix key has been pressed. So if I want to go to the next, if I want to go to the next, what do you call it? The next Tmux window, I can do Control B N, and previous Tmux window is Control B P. And also, if you want to go to the very last Tmux window that you were in, I believe that's Control B B. Yeah. So that's useful if, let's say, I've scrolled up here and I wanted to take a look at my Linux install list. This is a list of um, programs that programs and libraries and fonts and whatever else that I would need to install after doing a fresh Linux install. So I've just maintained this list here. Another thing I'm exploring, actually, because my list is so long, something that I wanted to explore is, give me a second. There. Something I wanted to explore is using Docker. Because Docker, I've noticed Docker is great for situations where you wanna isolate programs that you're running. More specifically, you wanna isolate their dependencies, because it allows you to create this environment in which the program would be running, or kind of an environment. It's still using your at least from my understanding, it's still using your system's kernel, right? But the quote unquote operating system that it's using and the dependencies and libraries and stuff that it's using, you get to define all of that within a certain environment, and then your program is going to be using those. So this way, you don't need to install those dependencies and libraries and whatever extra stuff. You don't need to install all of words. You don't need to install all of that in your host operating system. You can just make it part of the Docker image, and then your program can run within this Docker image. The great thing here is that you're not limited to just this one program being within that Docker image. Turns out you can set up like an entire OS environment within it. Of course, there's a lot of different limitations there. Um, in terms of what you can and cannot do. However, you can set up quite a lot over there by defining everything within the Docker image. And then you can move this Docker image from one machine to another. And this way you'll be able to move your tools. You'll be able to have a portable toolbox, essentially. Because like in my case, for example, I have, wait, let me close this. window delete. Okay. In my case, for example, I have a bunch of things, right? I have Zoxide. Actually, I should look into how well something like Zoxide would work, because Zoxide has this interactive thing, right? And this it maintains a database that it's constantly updating, because it is hooked into whatever events get fired when, not whatever, but certain events that get fired when you use something like CD. And after that, it builds this list, so you can then yeah, so you can then easily access them from this list. However, I don't know how well it's gonna be, because here's the thing: the thing that makes doing this within, oh, sorry, hit my mic stand. The thing that makes this so powerful within, or sorry, the thing um, that makes Docker so powerful, and gives it the ability to do this, is the fact, or well, I shouldn't talk about what's giving it the ability, but rather what that ability is. This allows Docker to pretend like this environment is the environment that the program is running in. In reality, like, it's not like a virtual machine that you're running. So that's why there's a whole bunch of, let's say, pretending that has to be done, a whole bunch of like tricking that has to be done. And Docker manages to do that, to make the program use the specific dependencies that you have selected. And it's not just dependencies, there's a bunch of other things that you can also run. And you can essentially set up an entire OS within that image, and then on top of that OS you can have a bunch of other programs and stuff. And the major advantage of this is that you're not going to have to install any of these programs within whatever other machine you're trying to run it in. However, you will still be able to access files on a certain machine, or whatever the host machine is. You will still be able to, I believe you can also access like environment variables and change environment variables and stuff like that. Like I said, there are like limitations as to what you can do, because you are, after all, not running this on the host operating system. You're tricking whatever the programs are into using your separate uh, OS that you have set up. But yeah, I need to explore Docker at some point, because it's a pretty interesting concept. Like, initially, I was hearing about Docker mainly in the context of running individual programs. So a lot of open source projects, when it comes to like testing out their application, or well, running their application, they would give you different methods of installation and running. One of the methods would be Docker. So they would provide you with a Docker image, and you can just run that. So within that image you have the base OS setup. Maybe, I think so. I believe each each image has a base OS kind of thing set up. um, and then you have the dependencies that the program requires, and then of course you have the program as well. um, and again, the advantage there is that you're running this as like an isolated kind of thing. You're not changing the dependencies of your host operating system. So this prevents stuff like, having conflicting dependencies, or changing breaking dependencies. Let's say that. You can have different versions of different libraries set up. And that's why I want to. Okay, so I was talking about like, oh yeah, I was talking about how I've only seen Docker being had I had only seen Docker being mentioned in the context of running specific programs, right? But then in terms of setting up an entire OS within the thing, or I shouldn't be saying setting up an entire OS, more so being able to run multiple programs within one image. So this way I can create like my own, little toolkit that I can move from one computer to another. I have never actually seen that, or I should say, I have never actually looked into that, or even more accurately, prior to my recent research on Docker, I hadn't looked too much into that specific aspect of Docker, where you can set up multiple tools and basically set up like an entire OS kind of thing, instead of just one program with all of its dependencies. So learning about that, it was pretty interesting. At some point in the future, I would like to explore that a lot more. I've also been doing research on home labs. I've also been doing research on home labs, and dude, it's pretty interesting the stuff that people come up with. It is really interesting. The things that people come up with. What blows my mind is the modularity of all of it. Because with a home lab kind of system, you could have like, let's say, a think center. You could have a couple of Raspberry Pis. um, in terms of computing, I'm just going to stop it there. You can have a think center, which is a slightly bigger machine than a Raspberry Pi, but it's still pretty small, more so flat. You can have a think center. You can also have a couple of Raspberry Pis. So you already have a couple of computers there, right? You have, you can have all of these computers set up within a network, and not even in a network. You can have all of these. Well, technically, yeah, it's going to be in a network, but you can use something like Proxmox to set up either VMs or Linux containers. And these Linux containers can be running on these different hardware platforms, these hardware devices that you have, these different computers that you have set up. And all of that can be controlled from like this one interface that you would access through your browser. And there's a lot that you can do with something like that, because all of that can then be connected to a network switch, which can then be connected to your router. And you can also, I saw, I would actually like to explore this as well. I saw somebody had set up basically an external storage using multiple SSD drives, or NVMe, or whatever, those SSDs, the small SSD drives that are very common these days in terms of hard drives. They had set up like a cluster of them as one, and they were able to use that over the network. So I'm assuming it was something like NAS, something like network attached storage, or maybe it's something more sophisticated than that. I'm not sure. um, and that, like, all of those machines were able to use that one thing. I think there's a certain level of like partitioning going on over there. Proxmox handles like a bunch of this very complicated stuff, because I feel like the real power of Proxmox is not just in the fact that it's able to handle, or it's not in the fact that it's able to handle just one system. You can have multiple systems set up, and all of them can be configured and managed and used by this one Proxmox instance. That's the crazy part for me. That is insane, dude. And then you can set up like various services to run in places. You can set up Linux containers. Linux containers are more like, so with Linux containers you would actually be sharing the kernel. It's essentially a very lightweight OS that's sitting on top of, um, I was about to say sitting on top of the kernel, but it's more so it's running on top of Proxmox. However, you can have multiple of these very lightweight kernels, which are more or less their own operating systems, but they're all using the same kernel. They're not all running their individual kernels. And dude, there's just so much to explore with home labs. I wish, I wish I had a way to get Raspberry Pis cheap, because where I live, I'm better off just ordering the Raspberry Pi online, because if I try to buy it from a shop somewhere here, it's gonna be the because like they order it online as well, right? And then they have to pay import duty, so then that makes it a little more expensive. Then they have to do their own markup to so they can get some profit. So then that makes it a little more expensive, and by the time by the time it gets to me as a oh, by the time it gets to me as a consumer, you could say I would probably be able to buy three Raspberry Pis online for the price of two over here. So I'm better off just buying it online at that point. But even keeping Raspberry Pis aside, just in general, a home lab setup is what I want to try working on, and I want to look into those Think Center computers. I want to try getting one of those for myself, because that would be a nice first step in terms of setting up a home lab. At least I think so. Holy shit, dude! We've been having a yap sesh for a good like 31 minutes now. Give me a second. I'm gonna take a short break, and when I get back, we're gonna start learning about PWM. And I just realized this. I muted the mic and then I kept on talking. I don't know how much didn't come through, but what I was saying is, not to jinx this, even though I don't believe in jinxes, but not to jinx this. But we haven't had. I don't think we've had a single glitch today, with the RTMP feed. Um, and we also haven't had any dropped frames today, so that's good. That's great. I am starting to think that it might have been an issue with my laptop itself, um, because the only difference here is that I didn't have to. I let the laptop sort of hibernate, and then I had to switch it back on, which took me into the boot menu, and then I had to boot back into Windows. Though it wasn't like a full reboot, it was just resuming Windows. But that little bit of, thing happened in between that might have made a difference. Anyways, I mean, we're doing good now, so yeah, great. But yeah, I'm gonna take a small break for a couple of minutes, and I will be back. All right, I am back. Let's refresh this feed and then we will continue reading. Hold on, what am I doing? There. Okay. All right. So, we were here. We got done reading this, okay, and then we were moving on to the calculation. So, calculating PWM duty resolution. So, the duty resolution, does that mean the resolution? No, this means the resolution of the entire cycle, right? I'm assuming that's what they mean by duty resolution. Okay. In the ESP HAL, we need to specify both the duty resolution and the frequency when configuring the timer object. Therefore, it's important to understand how to calculate the duty resolution from a desired frequency and how to determine the frequency based on a given duty resolution. Okay, 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 I'm kind of getting that. Let's wait. Therefore, it's important to understand how to calculate the duty resolution from a desired frequency and how to determine frequency based on a given duty resolution. Okay, all right. These are the formulas taken from the ESP32 TRM, but the variable names are simplified. Okay, okay. That's why, because I was wondering, like, okay, why does this have different names? Like yesterday when we were going through this, when we were going through the PWM section in the ESP32 TRM, I was wondering why these names were different, but then the formula looked pretty much the same, and this is the reason. Dude, I'm so glad that we took the time, even though in certain cases the deep dive um, only made me realize that I didn't need to do the deep dive, but then in some other cases the deep dive 100% helped me. I'm so glad that we did the deep dive, going and diving into the TRM, trying to understand clock management, trying to understand what clocks are in general, what a clock signal is. That whole concept was like really very. That was very educational for me. That was very interesting to me because stuff like, okay, we have we have this crystal that generates a clock signal. What exactly is a clock signal? And then we have the concept of like, oh, okay, so this clock signal, whenever there's a rise or whenever there's a drop, the hardware is hardwired to respond to that rise or that drop. I believe it's mainly a rise. It's programmed to respond to that rise in a very specific way, and that rise is what gets counted as a tick, right? But even that ticking hardware, the hardware there is responding to the signals in a certain way, right? And then these ticks that are being registered, these ticks later on get these ticks are later on used to count time. They're used to create the notion of time within the ESP32 because the ESP32 by itself doesn't have any notion of time. So you use these ticks to create the notion of time, and then based on that notion of time, we have actually I was about to say based on that notion of time, we're able to create a frequency, but then they're all kind of interconnected, right? Because if the crystal is creating, if the crystal is oscillating at 80 megahertz, that is 80 million cycles per second, right? So that means 80 million ticks per second. If one cycle is one tick, that's 80 million ticks per second. And then we divide that to find out how many seconds is one tick, and we then find out that one tick is 12.5 nanoseconds if our um, frequency, if our clock signal frequency is 80 megahertz, then one tick is 12.5 nanoseconds. So now, thanks to this frequency, we have the notion of time, because now we know that in 1 second, we have 80 million ticks happening, and one of these ticks is 12.5 nanoseconds. So with a certain number of ticks, we would be able to represent, 1 second, 2 seconds, half a second, or whatever like that. And then this clock signal gets propagated further and divided down or scaled up or whatever. I think it's first scaled up because it goes into the PLL. Though actually that's not entirely true. As we have learned, um, with both, I believe with both the CPU and the APB, but definitely with the CPU as well, you are able to select the clock source, and XTL clock is one of the signals that you're able to select. PLL clock is another one. APLL clock is another one, and I forgot what the fourth one is. But yeah, you can definitely get the clock signal directly from XTAL. Um, but yeah, all of this deep dive that we've done, it has been incredibly helpful, because now I feel like I have a better, maybe not a full understanding, but I have a much better understanding of how these things are working, how the clocks are set up, how the clock signals are being created, how they're being used, how they work in general. It is incredibly interesting, and once I've gotten better with analog electronic stuff, I definitely want to try and set up my own clock signal kind of thing. More so something that reacts to clock signals. So I can generate a clock signal using a 555 timer IC. I believe you're able to create like a stable clock signal with it. I feel okay. That would be something interesting to look into. Like, is there instability in 555 timer IC? That would be. Hold on. Let's open this up. Let's open this up. Let's not do that. I accidentally did that. Okay, let's close this. Yeah, now let's open this. Hey, so I'm wondering, is the signal generated by a 555 timer IC always stable, or is it not the most reliable thing? The 555 timer IC is a legendary Swiss Army knife of electronics, but its stability really depends on how you define reliable. While it is remarkably robust for general timing, it isn't a precision instrument like a crystal oscillator. Okay, whether it stays stable depends on three main factors. Component tolerance. The frequency of a 555 timer IC is determined by an external resistor capacitor network. The problem, most capacitors have oh yeah, if I'm using those bigger capacitors, and just in general the cheaper capacitors, because most of them they have they give a little window of tolerance, so the resistance that you're getting is not perfect resistance. um yeah, that tolerance thing, or I should say the inaccuracy of those resistors. Usually that's not a very big problem. However, when you are doing like what Gemini said, precision stuff, you kind of want proper precision. You can't really uh having bigger windows of error, bigger margins of error. It doesn't really work out that well, because that's how you'll get these inaccuracies. Anyways, let's continue reading. Furthermore, electrolytic capacitors can leak or change value as they age. The result, if your components drift or heat, no, if your components drift because of heat or age, your signal frequency will drift right along with them. Then temperature sensitivity. The internal design of the 555 uses comparators and a flip-flop. While the IC itself is relatively stable across temperature ranges, the external RC components are not. Standard resistors and capacitors expand or contract with heat, which slightly alters their electrical properties. In precision applications like a clock that needs to be accurate to the second over a month, a 555 will likely drift by several seconds or even minutes due to ambient temperature changes. Power supply noise. The 555 timer is notorious for creating voltage spikes on the power line. When the output switches states, it creates a massive, though brief, current draw. Without a decoupling capacitor, usually 10, I think that's microfarad or picofarad, I'm not sure. Um, Usually a 10 microfarad, is that micro or pico? Hold on, I don't want to keep saying the wrong thing. Micro versus pico symbol. It is micro. Okay. Oh, pico is P. Um, Nano is N, and micro is a U because milli is an M. Okay, all right. Right, back to this. Without a decoupling capacitor, usually a 10 microamp, a 10 microfarad, and a zero point 0.1 microfarad placed very close to the close to the chip's power pins. These spikes can interfere with the chip's own internal threshold levels, leading to jitter or double triggering. Comparison 555 timer versus crystal oscillator. Okay, you know what? That's okay. That's fine. Dude, hold on. Hey, this got me wondering, is there any way at all I would be able to use, though this would probably require me to combine circuits together. I don't know if that's gonna work out. Yeah, yeah, that's probably gonna require me to combine circuits together. No, wait, oh, I could do something here. I could try using an optocoupler. I could try that. I could try that. Though, now that I'm thinking about it, could I not just directly? So, okay, my idea was this. What I was going to ask Gemini was that, hey, is it possible for me to read the XTL clock directly from the ESP32 and use it in another circuit? Okay, hey, this got me wondering, is there any way at all I would be able to use the XTL clock um, from the XTAL on an ESP32 dev board um, directly in another circuit? And would this require combining um, the circuits together? The short answer is no, you cannot tap into the XTL clock pins directly, but there is a much better way to achieve the same result. Why you can't use the pins directly? The crystal oscillator, XTAL, on the ESP32 dev boards is connected to the chip via two pins, usually XTAL P and XTAL N. Delicate balance. These pins are part of a high-frequency analog feedback loop. If you attach a wire or another circuit to them, the added capacitance and impedance of your wire will likely cause the crystal to stop oscillating or drift wildly in frequency. This would crash the ESP32 instantly. Um, and weak signal. The signal directly at the crystal pins is usually a low voltage sine wave, not a clean square wave. Okay, that's something worth taking into account. meant only for the internal silicon. It's not strong enough to drive external components. The solution, use clock out. The ESP32 has an internal clock tree that can route various internal clocks, including the highly stable 40 megahertz crystal frequency, to specific GPIO pins. This is a standard way to provide a stable clock to an external chip like a camera, an external DAC, or another MCU. On the original ESP32, you can route the internal crystal to GPIO 0, 1, and or 3 using the internal clock signals, the internal clock out signals. How to do it? You don't need to combine the circuits physically at the crystal level. No, at the crystal. Instead, you connect a single jumper wire from from the designated um, ESP32 GPIO pin to the clock in pin of your other circuit. You must also share the common ground between the two circuits. Yeah, that's what I was talking about when I said when I asked if I need to combine the circuits. I was asking if I need to share the pin. I'm trying to keep it isolated. You know what? It's fine. It's okay. We don't need to worry about this too much right now. For now, let's continue reading this. Okay. Holy shit, that was a tangent, dude. Damn. Okay, all right. Formula for PWM signal frequency. The frequency of the PWM signal, FPWM. Okay, here we need to open up this because I did write this down. So the formula for, where was I? The frequency of the PWM signal, FPWM, can be calculated using the following formula. So we need LEDC clock. LEDC clock is the frequency of the clock source for the PWM timer. Okay, okay. So that's going to be 80. Is that 80? That's 80. That's 80. Also, I'm just earlier when I was talking about like clock signals coming in, I can't remember if I accidentally said that Xtal was giving 80 megahertz. I don't think I did. I did mention 80 megahertz. I don't remember if I mentioned Xtal in connection to 80 megahertz. If I did, then yeah, I didn't mean that. Because the 80 megahertz is not coming like directly from Xtal. Um, also, I hold on. Let's come back here because I'm curious about how we get 80 megahertz. So here we have the CPU clock. The CPU clock source can be set to either of these, and RC fast clock is the fourth one that I was not able to remember. I remembered XTL, PLL, APLL, but I couldn't remember RC fast clock. Okay, all right. So um, just a second. Okay, all right. So if so, how is this happening? How does this become 80 megahertz? Is there something that divides this? There's a mux somewhere here, right? If it's a PLL clock comes here. Um, that's his PLL D2 clock. There's a PLL clock. There should be something coming from the CPU. Well, I mean, this is all coming from like the CPU. Um, actually, no, this is not all coming from the CPU. No, I shouldn't say that. Um, what was I trying? Oh God, what did I just do? I accidentally hit like I was moving my finger around and tapping it on my like where I'm sitting. I accidentally hit the end key, and so it went to the bottom of the document, and then I hit the home key to go to the top of the document. Wait, maybe I have the things selected here and we can, let's look at the document outline. Actually, chapter 7 is what I'm looking for. 6, 7, 6, 7, system clock. All right. System clock. All right. So this is what we are looking for. Yeah, I don't know why I said that everything is coming from the CPU clock. I don't even know what I meant by that. I was trying to say something, but I wasn't trying to say that. I said that, which was wrong, but then I don't remember what I was trying to say. So, moving on from that, this is giving us like a hardware layout of how things are being routed. This mux is only going to the CPU clock. That's fixed, right? This mux is only going to the CPU clock. We have APLL clock. Um, I think so. These are signals. These are signals, right? APLL clock is coming from here directly in there. There's no mux in between. So yeah, that makes sense. APLL clock it's the exact same signal. This is called PLLD2 clock, I'm assuming because it was divided over here. And I believe I remember Gemini mentioning that the naming scheme of these things is chosen based on how often, like which kind of operation is done more often. And this div2 apparently, while it says div2 meaning, divide into half or divide by 2, it can actually divide by more. It's just that the thing is called div2 because apparently that's probably the most common operation. Okay, so coming from the PLL clock, if we have a clock source of 160, what are the speeds being mentioned here? So we have a PLL clock of 320 and 480. Okay, if um so if the CPU clock source is set to PLL clock, then this thing has an 80 megahertz. So I guess I don't need to understand. Well, I mean, I want to understand it, but like I don't need to go too deep into it. We can just understand that okay, if PLL clock is set to um, if the CPU clock source is the PLL clock, then we are getting 80 megahertz, which is the result of this. And I'm assuming div2 here, it could be more than just 2. So it's being divided by more than just 2. I'm assuming. I could be completely wrong about this, but I don't think I'm entirely wrong. Though, okay. We have APB clock coming in here. APB clock is coming from APB gen, right? And then that goes into this LEDC SCLK. Isn't that mentioned here? LEDC SCLK, or was that something else? There's LEDC CLK. What's the mux getting its thing from? So it could be RC fast clock, which is not the case for us. It could be APB gen. What is coming from APB gen? Let me ask Gemini. I'm reading the ESP32 TRM and well TRM chapter 7 reset and clocks, and I'm looking at the CLK management CLK management, what do you call this, block diagram, block diagram. um, I'm wondering where I'm wondering what APB gen is and where it comes from. In the ESP32 architecture, APB gen is the control logic responsible for deriving the clock signal used by most of the chip's peripheral modules. It acts as a bridge and a divider between the high-speed system clocks, and the individual peripherals that require a more stable or low-frequency timing. Where does it come from? The APB clock doesn't come from a signal from a single hardware oscillator. Rather, it is quote unquote generated from the CPU clock, which is the system clock. The system starts with a high frequency source, typically PLL clock or X-style clock, system clock. This source is scaled to create the CPU clock and then the APB gen logic. This block takes the CPU clock and applies a secondary configuration. In most standard operating modes, the APB clock is tied to the CPU frequency, but capped. If the CPU is running at 80 megahertz, the APB clock is usually 80 megahertz. If the CPU is overclocked to 40 megahertz, the APB gen logic ensures the APB bus typically remains at 80 megahertz to maintain compatibility with peripheral timing requirements. What is its function? The APB Gen block provides the clock for the APB bus, which is connected to communication interfaces like UART, SPI, I2C, and I2S, timers such as general purpose timers and watchdog timers, and control modules such as PWM and remote control. All right. Sorry, zoned out. Okay, all right. Holy shit, this has been the first time that I zoned out during today's stream, dude. I'm just realizing that. This has been the first time that I've zoned out during today's stream. We are an hour into the stream, and this is the first time that I've zoned out. I think so. I think so. No, no, no. Yeah, this is the first time that I've zoned out during today's stream. I've just been like yapping away the entire time. Oh, I think the reason was because I was yapping away the entire time and not absorbing knowledge from somewhere else. Yeah, yeah, that might be it. Hold on just a second here. By the way, dude, this Z-swap thing that I set up, dude, it has been super helpful. It has been super helpful. This machine, this 2 GB DDR2 machine, on which there were various live streams that I was not able to watch before. I mean, I was able to watch a good chunk of Twitch live streams, but there were certain live streams that uh, I wasn't able to watch because the moment I would load them, for some reason, the tab would just start eating up my RAM big time compared to other live streams. I was never able to narrow down why exactly that was, but that's what it was. That was the issue. I knew that. I knew this much that it was those specific live streams had something going on which would cause the tab to just eat up a lot of the memory. And on a 2 GB DDR2 system, I'm already really memory constrained. So, if there's a memory spike in or memory usage spike in one of these streams, I'll notice it. The system will notice it and it's going to start to struggle. And now, ever since I um, set up ZSwap, I've had very few such issues. I do have it every now and then, um, but it is not nearly as bad as it was before. Like not even remotely close to as bad as it was before. The system has become a lot more responsive now, and holy shit, dude, I'm glad that I took the time to do this. This is crazy, dude. Okay, all right. Now, back to this. I find myself being curious about like how we are getting this because all right, we have APB Gen. APB Gen is going into this PLL D2 clock. Is that, do they mention uh this anywhere? There's peripheral clock. Oh, is this the D2 clock? I think this is the D2 clock. Hold on. I think this was mentioned somewhere. This was mentioned somewhere. D2 is the one that's not, yeah, D2 is the one that's not being mentioned here, right? So what figure are we on? This shows which clock can be used by which peripherals. Okay, D2 can be used by PWM. Okay, APB, so and so, so and so. Right. What about this? This is divided from the so and so by automatically adjusting the clock division, and its frequency is always 160. Oh, its frequency is always 160. So if this was the one that's going in, then the frequency would not be 80 megahertz. It would be 160. Okay, okay, all right. Let's continue with this. Right. So it could be coming in from any of these places. Clock divider is the division factor for the clock source, and then res bits is the duty resolution in bits. Okay, all right. I do not remember. I think they mentioned that we would need to specify the PWM frequency and the resolution bits, but then LEDC clock, we don't decide that. That just comes in, and we are assuming that that's going to be 80 megahertz, but it's good to keep the timing in mind. It's good to keep all of this other logic in mind so we can determine. um Actually, they mentioned something down here, right? PWM frequency. Okay, APB clock the APB clock frequency is going to be 80 megahertz. Okay. Okay. Yeah, I guess after all of this has been explained, we come down to this, which is apparently the most common PWM frequencies, and we can just use one of these. I probably should have made the browser bigger for this because we haven't started doing any coding yet. So I probably should have made the browser bigger. Yeah, I'm gonna transition back. Right. So calculating duty resolution. Okay. Res bits is the duty resolution in bits. Okay. PWM duty resolution formula. That is, we have mentioned it here. Dude, I love looking at the trail. This is this is great. Okay. This formula is derived from the previous formula to calculate the desired duty resolution. This formula gives the duty resolution in bits, which represents the number of discrete levels available for the duty cycle of the PWM signal. I feel like when they use the term duty cycle, it becomes a bit confusing because notice how it says here duty cycle 50%, right? When they say duty cycle, they're talking about the percentage of time, the percentage within that cycle, within that one period, that the signal remains high. So when they call this duty resolution, where was it? This formula gives you, yeah, discrete levels available for the duty cycle of the PWM signal. So after having done all of this research, what I understand is that when we are calculating the resolution, we are calculating it for this entire cycle. We're not calculating it only for the duty cycle. So I guess that's why when they use this terminology, I don't know if it's accurate, and if it is accurate, then maybe it's just confusing to me. Maybe it's not confusing to anyone else. I don't know. Okay, this formula gives the duty resolution in bits, which represents the number of discrete levels available for the duty cycle of the PWM signal. Okay, so this is for one period, I'm assuming, because resolution in bits, we are usually like that's where we use the resolution, right? We are not usually using it for the entirety of. Actually, are we? Are we? No, hold on. If it is 80 million, okay, um, let's go here, I guess. Let's do Python 3.13. Huh. Let's say we give 1024. Yeah, 1024 multiplied by this and this and this. Is that going to fit within 1024? 2 raised to the power 1024. That's not 2 raised to the power. 2 raised to the, oh God. Okay. Did I do that right? Did I? No, wait. Did I do that right? So that's okay. That makes sense. If we are giving 256 bits, okay. Holy shit. That is, oh, wait, wait. What am I doing? We are limited. It's not 1024 bits. That's crazy. That's why the number is that big. That's crazy. It's not 1024 bits. So we have a max of like, isn't it a max 20-bit register? I think so. Yeah, I remember there being a limit. I remember there being a limit. And I remember that that is also why we are dividing down the APB clock signal, because this is one, this is 1,048,576. So let's say 1.05 million, right? So we can fit in 1 megahertz worth of, is that it? Really? Is that the max? I cannot remember what is the limiting factor here. It has to be the counter, the counter registers resolution, right? Or the counter registers. Yeah, here. Okay. The timer counts. Wait, PWM so and so so and so. This is determined by the number of bits used by so and so. Timer orientation stored in a register. Okay, it counts from 0 to a specified maximum value, then resets and starts the cycle over. Okay, so the counter register. So if we do 8 bits, we get 256 values. If we do 10 bits, we get 1024. That's where 1024 came from. Okay, that's where 1024 came from. Now, if we do a max of 20 bits, I don't know what the max resolution is. I don't remember where I got this 20 thing from. I got it from somewhere. It was definitely mentioned in the TRM as well. Like one of the registers there is a 20-bit register. That's a counter register the within the PWM like block diagram. That is max 20 bits. But it was also mentioned somewhere here, and I can't remember where that was. Okay, all right. Anyways, let's carry on. So we got the duty resolution formula, then calculating the highest resolution. The highest resolution is achieved when the clock divisor or clock divider is set to 1, meaning no division is applied to the clock. It is calculated as um, log 2. Wait, let's try this. Import math. Um, import math.log, I guess. Log 2. Yeah, we have log 2. Okay, let's real quick try this. Okay, so then 16 should give us 4. Yeah, okay. Um, clock, LEDC clock. LEDC clock is going to be, it's not the scaled version, right? That's the clock source. So we are going to do 80 million um, divided by, wait, multiplication, then division. Yeah. Divided by FPWM. The highest resolution is set when so and so. Okay. FPWM. What if we want, let's say we want 1 megahertz. So we want 1 million cycles. I don't know what this means. This calculation gives the maximum number of bits that can be used for the duty cycle. Oh, we can only use 6 bits for one duty cycle. We can only use 6 bits. So 64. Okay. So then our counter is going to be limited to 64 in that case. Okay. All right. So with 1 megahertz, we can do that. Though, okay, um, 64 is not that bad. Yeah, 64 is not that bad. But like keeping that in mind, I'm a bit confused here because we are able to do 1 million with a resolution of 64. Okay, we're able to do 1 million ticks per second with a resolution of 64. But then with a resolution of 20, is this a resolution of 20? No, hold on. We are able to do 1 million. I keep confusing resolution bits and the actual resolution. Though, okay, no, it's not. No, no, no. Resolution bits is the resolution. That's the resolution we are setting. So here we are talking about a 6-bit resolution, and we are saying that a max. I still don't remember where I got this 20, this value of 20 from, but let's say 20-bit is the max. Okay, 20-bit is the max. That means we can. Oh, oh, 20-bit is the max. That means we can have these many ticks per duty cycle. This is not the total. This would be per duty cycle. And that is extremely um, fine, that is extremely like granular, very detailed, it's probably also going to be slow. Yeah, I think there might be some issues there. I don't The problem is I can't remember what I can't remember at this point. Like there was something that like there was a calculation that I had done at the very beginning when we were learning about this stuff, and I was having a conversation with Gemini about um, how these calculations work, because initially I wasn't able to make a whole lot of sense out of this. Okay. Example, for a 1 kilohertz PWM signal, 1 kilohertz means 1000 cycles per second. So we're going to have 1000 periods per second. Um, our highest resolution. So thus the highest resolution for a 1 kilohertz PWM signal using an 80 megahertz clock is 16 bits. Okay, so I guess here I need to understand that yeah, we need to have like a source clock signal, a source clock signal frequency, and then out of that we are generating our PWM frequency, right? The PWM frequency is being generated using this. So let's say it is, hold on, APB underscore CLK equals 80 uh, million. So that's our APB clock. Um, and we have a clock divider. So I haven't, yeah, we haven't set up a clock divider here yet. So I guess I don't know how the clock divider is like fitting into this. Let's say there's no division, okay? Let's say there's no division. Let's say CLK underscore div equals 1. And we want to do FPWM equals APB clock divided by 1 multiplied by exponent comes before multiplication. Yeah, okay. Multiplied by 2 to the power 16. So FPWM is that. Um, hold on, hold on. This is our frequency. This is okay. Um, there's a lot of zeros in there, so I'm gonna have a little trouble counting that. Is that 7 zeros or 6 zeros? Let's say 7 zeros, okay? So that's 1,000, then that's a million. Okay, so that's 880 million, 242 billion. So 5,242,880,000,000. That is if we don't divide it down. Okay, they haven't mentioned what the division factor could possibly be, but let's say it's this. That just took one zero out. So that doesn't really help. Um okay, wait. Let's continue here. Um Calculating the highest. Okay. Okay. Okay, calculating the lowest resolution. The division factor ranges from 1 to 1023 as per the data sheet. Okay, all right. The lowest resolution is calculated when the clock divisor is at its maximum value. The lowest resolution is calculated by the clock divisor when the clock divisor is at its maximum value. In this case, the clock divisor is 1023 plus 255 divided by 256. So the lowest resolution is calculated as so and so. This calculation gives the minimum number of bits required for a duty cycle control to be for a duty cycle control at the specified PWM frequency. I didn't understand what this means. Yeah, I didn't understand what this means. Um, Also, this seems to be saying 6.28, which is close to the value that I got up here somewhere. I got 6.32. And I was doing, this is multiplied by 1000. Oh, 1000 multiplied. So 1000 is what no, how are they getting these values? I'm guessing 255 divided by 256 is 0.996. Yeah, it's 0.996. So then we get 1023.996, and then 1000 is supposed to be what exactly? Our PWM. Okay. So then we get this value, which I had gotten up here. So if I do APB underscore clock divided by 1023,996, that's, oh, not 1023. It's 1,023,996. We get this. Why is that? Oh, because it's supposed to be log 2. So we do math.log2, and then we get that. Okay, that's interesting. That's interesting because what it mentioned, like now I'm wondering if I got this calculation right or wrong because I set, so PWM, I set it to a million, right? I said 1 megahertz, basically. 1 megahertz multiplied by a clock divisor or clock divider, clock division factor of 1. So that's 1 million. And if our LEDC clock is APB clock, it's going to be 80 megahertz. So 80 million divided by 1 million, and then that gives us, well, log 2 of 80 million divided by 1 million gives us the highest resolution. But then how is this formula giving us the lowest resolution? Yeah, I'm kind of confused about the math being used here. Or I probably haven't understood the meaning of lowest resolution and highest resolution here. So like given for a given frequency, let's say, for words, for a given frequency, um, so addition is not going to be done first, right? So we need to group that up. Let's say h res equals log 2 APB clock um, divided by what frequency did I say? Okay, let's say 1 kilohertz. Okay, one wait PWM. Let's say f underscore PWM equals 1000. Okay, so then h res equals math.log2 um what was it? APB clock divided by f PWM multiplied by, so we don't need to recalculate this whole thing. We can just do, um, what is our thing? Oh, yeah, okay, okay. We can just do 1023 multiply 1023.996. Okay. HRes is 2026. Okay, that's our highest resolution. Okay. Now let's do LRes. I was just calculating LRes. Holy shit. Okay, fine. We just did LRes. Now let's do HRes. HRes is equal to math.log2 APB clock divided by this. So that is our F underscore PWM. Okay. LRes. Can I do a comma thing here? Would that work? Oh shit. Okay. Presents it as a tuple. Right. So that's interesting. Our lowest resolution comes to 26 bits, but our highest resolution comes to 16 bits. Something is wrong here. Something is wrong here. Something is something is wrong here. Yeah, no, I'm missing something here. Let me open up what is it? ESP32, Impel Rust, dev environment, and so and so. Let's open this. You need to scroll down to PWM, LED PWM controller, and then here I need to take a screenshot of this. Okay, let's do that. Just a minute. I am okay. I'm learning about LED PWM for the ESP32. I'm having trouble understanding these formulas because using an F underscore PWM of 1000, I get a lowest resolution of 20, what were the values? 26, and highest resolution of 16. Yeah, 16. How is the lowest res somehow higher than the highest res? It can be quite confusing at first glance because the math seems to move in the wrong direction. The confusion usually stems from how we define resolution in the context of PWM. It's not about the frequency itself, it's about the number of discrete steps you can fit into a single cycle. Okay. Yeah, that still doesn't make sense. So the lowest the lowest resolution, Back up, back up. Did I miss something here? There's log 2 and this and this. I feel like I missed something here because I just noticed that here it says 16 bits, which is fine for the highest resolution. For the lowest resolution, I'm getting a different value here. So I'm feeling like I messed up somewhere because it's supposed to say 7 bits here. APB clock divided by, um, hold on. LED, so and so, so and so. Okay, okay, okay. Yeah, yeah, I'm not getting it. So the division factor ranges from 1 to 1023. As per the data sheet, the lowest is calculated when the clock divisor is at its maximum value. In this case, so and so. Yeah, yeah, no, I'm confused about this. Hold on. Okay, here's a breakdown of why the numbers appear flipped. Defining the highest resolution. In PWM, resolution refers to how many bits of control you have over the duty cycle. Highest resolution, 16 bits. Example, 16 bits. You have 2 to the power 16 possible duty cycle steps. Okay. This allows for incredibly smooth dimming. Then low resolution, example 8-bit, you have only 2 to the power 8, which is 256 steps. This jumps between brightness levels. No, the jumps between brightness levels are much more noticeable. Okay, the relationship between frequency and resolution. This is a fundamental physical trade-off in microcontrollers. As the PWM frequency goes up, the available resolution goes down. Think of a single PWM cycle as a bucket of time. I get this. Okay, mathematically, you likely arrived at that by using a different clock source or a different divisor. But here's the logical correction. Highest resolution is in your formula in your formula refers to the theoretical maximum bits you can achieve. Okay, the misunderstanding. If you calculated a value of 26, you are likely looking at the hardware limit for very low frequencies. However, if you increase the PWM frequency, the math forces that bit depth down. I don't think Gemini is understanding what my problem is here. I don't think Gemini is understanding what my problem is in this case. This is 16 bits. Okay, hold on. What did I give? Oh, oh God, dude. I did not give Gemini the entire thing. Hey, I just realized that I only gave you the formula um, mentioned for high res or highest resolution. I didn't give you the formula mentioned for lowest resolution, so you cannot see why I'm confused here. Let me, oh, wait, no. Here is the formula for lowest resolution. Okay, give me a second, or give Gemini a second. Okay, this new image clears up the confusion clears up the confusion perfectly. The reason the numbers seem backward is because of a subtle but important distinction in what these formulas are actually calculating. In the context of the ESP32 LED-C peripheral, these aren't limits for the hardware in general. They are the limits of the clock divider for a specific frequency you have chosen. The real meaning of highest versus lowest. The ESP32 uses a clock divider to slow down the main clock, which is 80 megahertz, to reach your target PWM frequency, which is 1 kilohertz, so 1000 hertz. Highest resolution divider is equal to 1. You are running the PWM timer as fast as possible. This gives you the maximum number of steps, which is 16 bits, to describe one cycle. All right. Then lowest resolution, divider equals max. You are slowing down the clock as much as possible. Because the clock is crawling, you can only fit a few ticks, about 128 ticks or 7 bits, into the same 1 kilohertz window. The range of choice for a 1 kilohertz signal, the ESP32 hardware you a working range gives you a working range. You can set your resolution anywhere between 7 bits and 16 bits. If you try to set it to 20 bits, the clock isn't fast enough. Um, it's physically impossible. Okay. If you try to set it to 4 bits, the clock divider can't go high enough to slow the clock down that much for a 1 kilohertz signal. Why the result is 7, not 26. In your previous message, you mentioned getting 26. That likely happened because you were looking at the formula for a different frequency or calculating the absolute maximum the register can hold. You know what? Let's see. I might have made that mistake. Hold on. Calculating the highest resolution. Okay. Let's take a look here. So HRes, I have set it to log 2. Okay, APB clock. APB clock, just to be sure, it is set to 80 million. Yes. Okay, APB clock is set to 8 million. Um, so then our highest resolution calculation is fine. It's correct, right? Now, what went wrong here? Yeah, what exactly went wrong here? Because so LRes, okay, multiplication gets done first, then division is done. So we should be fine on that front. And then the log 2 is done. Is maybe log 2 being... Okay, let's do it this way. Nope, still saying 26. Okay, I have a doubt here. I've had this issue in the past. Okay, so I'm going to try something here. Import math math dot log 2. No, wait. Let's okay, and then let's do this 80 million, still saying 26. Okay, still saying 26. So we're going to try doing this here now. Okay, math.log2, 80 million divided by 1000 multiplied by 1023.996. Nope. Okay, it's not what I thought it was. I'm confused. Um, okay, so I'm confused. Here in Python, I'm doing math.log2, 80 million divided by 1000 multiplied by 1023.996, 996, 993, 6, 996, um, and I'm getting 26.287706. 287706. Okay, I see exactly what happened. You've run into the classic order of operations mistake in your Python code. In Python, multiplication and division have the same priority and are evaluated. Oh, oh God, dude. I did not know that. See, the thing is, I have done this grouping thing for ages. For the longest time, I avoided doing doing like PEMDAS, so like parentheses, exponents, multiplication, division, addition, and subtraction. Like that's how you get the arithmetic precedence. But to avoid all that, I would just like start grouping everything into parentheses because that made things so much simpler. Holy shit, that is insane. That is crazy. Okay, well, we got our response, and we also learned something today in terms of arithmetic precedence in Python. That's crazy. That is crazy. Yeah, that's insane. Okay, well, now that that's cleared up, commonly used PWM frequencies and resolutions. This table is from the data sheet. This table is from the data sheet. It summarizes the highest and lowest resolutions for common PWM frequencies with different clock sources. Okay, all right. So I'm guessing I won't need to do these calculations every time, but these calculations are being explained just so that we understand exactly why we are having, lowest number of bits, highest number of bits, and why certain values may or may not work well together. So for example, um, let's say I set the clock source to, let's say I set the PWM frequency to 1 kilohertz, but then I try to set the resolution to maybe, actually, we have to be between the highest and lowest resolution, right? We cannot set something lower than the highest resolution because otherwise we won't be able to do 1 kilohertz. So like if I set the highest resolution to be, um, or if I set resolution bits to be 15, that's probably not going to work out. That's probably not going to, you know, it hopefully it might give an error. I think, okay, that would be worth experimenting with in Rust, on the Rust side, to see if that does actually give us an error. But that being said, we can now move on to motor controlled pulse width modulator. Okay, the ESP32 has PWM has two PWM peripherals, LEDC and MCPWM. In this chapter, we will introduce the MCPWM. MCPWM is designed for motor and power control. The ESP32 features two MCPWM units, MCPWM0 and MCPWM1. The diagram below provides an overview of a single PWM module. Okay, all right. Okay, APB bus, we get the clock. Okay, so it's 160. This one is running at 160. That's interesting. Okay, all right. Each MCPWM has a prescaler or clock divider, um, three timers, three operators, fault handler, and a capture module. Prescaler. The prescaler is used to reduce the base clock frequency before it's applied to the PWM signal. The MCPWM is driven by a clock um, with a frequency of 160 megahertz. I feel like um, it's worth at least exploring the TRM side of this. So let's see. Um, Hold on. Let this. Um, is it not called MCPWM? There's LEDC. Okay. Okay, let's do PWM. Let's just say PWM. That is 1,000 matches. We should not do that. MC PWM. Okay. Did I? Maybe I typed something wrong before. Right. Chapter 29. Was the previous one 28? Like, yeah, LEDC was 28. So, where are we in terms of chapters here? 29, PWM operator. Okay, LED, all right, okay. Okay, this goes into SD, MMC and stuff. Um, Two wire, okay, that's a communication protocol. Actually, that's one wire. What is two wire? Two wire is also communication, right? Yeah, it's a protocol for something. Two wire automotive interface. This is something else. One wire is a communication protocol. Pulse count controller. Okay, all right, okay. Um, One common topology uses a pair of PWM outputs driving an H bridge to control motor rotation speed and rotation direction. I do have H bridge motors. No, H bridge. Um, I believe they're H bridge. I could be wrong. I'll have to check again. But I do have LED, DC, not LED, DC motor controller modules. I do have those. And I believe this PWM, the MCPWM, is meant to help with communicating with those specific modules. Okay, all right. Sorry, zoned out. Okay, okay, every PWM timer has a dedicated 8-bit clock prescaler. There are three timers in each MCPWM module, and there are two MCPWM modules, right? I believe so. Yeah, yeah. Um, two MCPWM units, I should say. Okay, all right. I wonder if this is coming from here. Where is it? Because this is part of peripherals, right? So I wonder if this like PLL D2 clock is coming from here because this happens to be 160, right? And there's a separate LED source thing here. This is a clock source. This clock source is selected by the LED APB clock cell register in so and so. Wait, in 72.6. 7, sorry, 7.26. Oh, okay. All right. Never mind. Um, divided by the PLL clock. Okay, okay. It doesn't mention MCPWM anywhere here, so I'm not sure. Okay. All right. Let's continue reading here. The prescaler is used to reduce the base clock frequency before it's applied to the PWM signal. The MCPWM is driven by a clock with a frequency of 160 megahertz, meaning it ticks 160 million times per second. This clock serves as the base frequency for the MCPWM module. However, the prescaler modifies this base frequency by dividing it, effectively reducing the clock frequency that the PWM signal uses. To calculate the duration of each clock cycle, the we take the inverse of the frequency. Okay, all right. Yeah, same as what we did with the APB clock. So we did 1 divided by 80 million, and that gave us 12.5 nanoseconds, and this is exactly half of that, I guess. How is this half of that when the frequency here is double of that? Oh, because as this becomes smaller, sorry, as this becomes bigger, the amount of time that each cycle spends within a second becomes smaller. That's why. Okay. So we have 80 million, and when we double that, then the time that a tick takes becomes like half. Okay, this means each clock cycle lasts 6.25 nanoseconds. Okay, the PWM clock prescale register, 8 bits in the ESP32 allows you to adjust this base clock by dividing it. Okay, okay. Once the prescaler is applied to the base clock, it effectively reduces the clock frequency, the resulting PWM period is calculated using the following formula. PWM clock period, so and so multiplied by prescaler value plus 1. Let's say you set a prescaler value to, you set the prescaler value to 159, then it'll be this multiplied by 160. I don't understand why the plus 1 is there, but okay. So then that gives us 1,000 nanoseconds. To calculate the PWM frequency, we take the inverse of the period. The inverse is 1 divided by so and so. Okay. Give me a second. All right. Where was I? With a maximum prescaler value of 255, since it's an 8-bit value, I'm glad that they mentioned that because I was about to ask why is it maximum 255? But yeah, if prescaler is 8 bits, then yeah, you have a max of 255. Okay. All right. With a prescaler value of 159, the PWM signal will have a period of 1,000 nanoseconds and a frequency of 1 megahertz. Okay. With a maximum prescaler value of 255, you can achieve the PWM frequency of 625 kilohertz. Okay, in the ESP-HAL, the peripheral clock config struct in the ESP-HAL is responsible for the clock configuration of the MC-PWM. It offers two functions to initialize with a prescaler or a frequency. This functions automatically. This function automatically these functions automatically calculate the prescaler to achieve the 1 mega. Oh, okay. So then we don't have to do that. Okay. All right. With frequency, let's test this out real quick. In here, um, okay, so let's say let clock. I think I need to add this thing to my, well, it'll get added. Okay, let clock config equals peripheral, what is it? Peripheral clock config. Peri clock, no, it doesn't work. Peripheral, what am I missing here? Okay, let's try that. Nope, that's not it. Periph, um, I'm missing something here. Oh, they gave like an example in the next thing. Hold on. Time rate LEDC. Oh, this is for yeah, let's go to MCPWM. I don't know if they, well, they do have an example for the what do you call it? For a servo motor. Yeah. PWM and servo position, LEDC PWM code. There's no using statements here. Wait, no. Down, full code. Uh yep, I'm not seeing it here either. Yeah, I'm not seeing it here. I'm gonna have to Google this. Yeah, dude. Okay, okay. Hold up. We're gonna go back to this page. Where was I? MCPWM in the ESP32. This is where we, yeah, this is the page we're on. Okay, timer. The timer is responsible for counting up to a specified value referred to as the period, at which point it resets. And so basically our counter thing, PWM counter, and starts counting again. This helps control the timing or frequency of the output signal. Each timer has an 8-bit clock prescaler. It has 16-bit counter that can operate in 3 modes. In ESP-HAL, this is represented as the enum PWM working mode. There's increase, which is counting up, where the timer starts at 0 and counts upwards to the period value before resetting. There's decrease mode, where the counter starts at the period value and counts down to 0 before resetting. Um, and there's up down, counting up down, where the timer alternates between counting up and counting down, creating a symmetrical cycle. Okay, then in ESP-HAL, the ESP-HAL has a timer clock config struct, which lets you initialize, which you can initialize via the clock config instance. You need to call the timer clock with frequency function or the timer clock with prescaler with arguments, number of ticks in the period, the PWM working mode, and the target frequency. Okay. Example, to achieve a 50 Hz frequency with a base clock frequency of 1 megahertz, we need to calculate the cycle count for the period of 0.02 seconds or 20 milliseconds at 1 megahertz. The calculation will be so and so. Okay, all right. We are passing 99,999 instead of 20,000 because a function internally increments it by 1, resulting in so and so. I still haven't understood that one thing, the plus one thing that was mentioned up here. I believe that's what it, yeah, that's a pre-scaling thing. Yeah, I still haven't understood what that's for. I guess I can ask Gemini. Okay, all right. Operator. The PWM operator generates the desired output waveform using the timing references from the PWM timer. Each PWM operator features 2 outputs, PWM-A and PWM-B, with configurable dead times for both rising and falling edges. We have configured the MCPWM0 peripheral and selected operator 0 to use the PWM-A output. Here, the up active high sets up active high. Okay. Sets the up active high for the PWM action and sync on 0 for the PWM so on. So what this means, the output signal will be high when the timer count is less than the timestamp value, then the new timestamp will be applied when the timer reaches 0. I haven't fully understood what this is saying, but I'm gonna move on from that. We can come back to that later on when we are actually doing this practically. I feel like we're going to be coming back to this quite a lot, just for like reference. But yeah, a set timestamp function in ESP-HAL. The set timestamp function sets the time at which the PWM signal should change when the timer reaches the value passed. Hold on. The set timestamp function sets the time at which the PWM signal should change. When the timer reaches the value passed to this function, it updates the PWM signal according to the configured PWM update mode. In our example, we have configured up active high. Is this basically setting when when the signal should go high and when it should go low? So is this basically another way of setting the duty cycle? I'm getting that idea, but it says timestamp. It says timestamp. So like, are we counting the time in ticks? The signal will remain high until the timer count reaches 500. So that's the ticks. Okay, 500 ticks. Once it reaches 500, the signal will be low. Oh, okay. Yeah, that's exactly. Yeah, okay. The signal will remain high for so and so, and then it'll go, okay, all right. So that's interesting. So here we are not specifying a percentage. Here we are specifying the number of ticks that it should remain high for. The number of ticks that it should remain high for. The number of ticks within the cycle. I I just found myself mixing up 1 cycle and 1 second, and I should try not to do that because cycles per second is the frequency, and if we have 1 kilohertz frequency, it's 1,000 cycles, and 1 cycle is a certain number of ticks. I don't remember what the frequency was here. One megahertz. Okay. So with one, wait, to achieve a 50 hertz frequency, that's 20 milliseconds or 0.02 seconds with a base clock of so and so. We need to calculate the cycle count for the period of 0.02. How are we getting 20 milliseconds here? Are we like dividing 50 to achieve a frequency of so and so? So that's 20 milliseconds. No, hold on. Let's say 50 divided by, no, that's not it. Is it the other way around? Um, nope, that's not it either. There's something that I'm missing here. To achieve a frequency of, oh, wait, that's it. That's that's what it is. 50 hertz is that much. So we get the timing there, and then we do, oh, so then 0.02 divided by this would be, why is it showing up like that? That's odd. What if we did it? No, that's not right. Yeah, why is it showing up like this? Let's try what was it? Dot 2e. Yeah, let's try print f um what is it? 2e so and so so and so um dot 2e. I don't know if this is how you're supposed to, or was it dot 10f? No, there's something that I'm missing here. Um, Hold on. How to print out the how to print out to so and so um in Python. Um, no, I want to print the non-scientific value. 8f, format to 8 decimal places. Oh, 10f is 10 decimal places. Okay, okay. All right. What am I doing here? I don't get it. Um, this gave us, oh yeah. So 0.02 divided by 1 million. Uh, yeah, let's just not do that. Let's multiply this, and that gives us that. So that's 20,000 cycles per second, isn't it? Cycle count. No, not second. Cycle count. No, wait. We need to calculate the cycle count for the period of so and so. Okay, yeah. So the cycle count. Oh, the number of cycles in one. Yeah, we need to calculate the cycle count for the period of so and so. Okay, so we're calculating how many cycles are going to be within one period, which is not 1 second, it's 0.02 seconds. I very heavily confused this entire thing. All right. LEDC versus MCPWM. LEDC is designed for controlling LEDs but can also be used for general PWM tasks, making it ideal for basic applications like LED dimming or simple motor control. MCPWM is specifically built for motor control with advanced features like dead time insertion and fault handling, making it better suited for precise and complex motor control. Typical use cases Typical use cases of MCPWM peripherals as per the API reference document: digital motor control, example brushless DC motor, RC servo motor, switch mode based digital power conversion, power DAC, where the duty cycle is equivalent to a DAC analog value, calculate external pulse width and convert it into the other analog values like speed, distance, etc., generate space vector PWM signals for field-oriented control. For controlling a hobby servo motor like the SG90, LEDC is simple and sufficient, but MCPWM can also be used. We're going to use both. We're going to use both because I'm planning on getting into robotics, so I'm going to be using MCPWM a lot. So we're definitely going to be exploring both. Now, that being said, that's going to be it for today's stream. We made some good progress today. We definitely made some good progress today because now we're going to be moving on to LED fading effect. And this is where it's going to get interesting because we're going to be doing practical stuff now. And all of this stuff that we've spent the past 2 weeks trying to understand, we're going to be putting that to use. We're going to be putting that knowledge to use, and we're going to be using that knowledge practically to build something. Um, so yeah, I'm excited for that. I'm excited for that. Now today I need to make sure that I go back and um, continue reading the Forrest Mims book because now that I've started reading that, I don't want to push that to the side. I want to see it through. But in tomorrow's stream, we are gonna continue with this, and hopefully, we're gonna be doing something practically. Also, I'm just so happy about the fact that we are in the fourth month of this year, almost the fifth month. Like it's almost the end of April, and I've managed to stream for the majority of this year. I've taken very few days off, and I'm pretty happy about that. That was something that I wanted with this year, to stream a lot more often. Um, yeah, dude, I'm I'm happy about that. But yeah, that's gonna be it for today's stream. I hope you guys have a nice day.